Okay, take two. It was so boring, I had to go get some students. And so here they are. And we're going to be doing 4.1 is what we're going to be looking at. And so I'm going to go here to my paper view. I have some tea. I have some students. I have some pencil, a pen. I have your textbook. The reason I wanted to have your textbook is they're telling us here, it says that the area under the curve and the area under the velocity curve will give you displacement, and the area under the acceleration curve will give you velocity. And then I said, if you want to read some things about calculus, and you could go to page 1. So page 1 in your book, when I look back there, it's just like the preview of calculus. We actually went over it on the second day of class, and it talks about the area problem and the tangent problem. Well, we looked, and also limits. And so limits were, let's see, were they chapter 1? And then the tangent problem happened in chapter 2 and chapter 3. And then there is a relationship between the area problem and the tangent problem. So you saw that we were finding the antiderivative in 3.9, and it turns out that the derivative, the antiderivative, they're going to have something to do with the area problem. So they're going to be telling us about that. It's a big surprise in 4.3, but right now, know that they're going to be a relationship. So that's the reason I put 3.9 with chapter 4. And anyway, they go on to tell you that the area problem, this is on page 3 in your book if you wanted to read it, the area problem is the central problem in the branch of calculus called integral calculus. So that's what we're starting to look at. It's important because the area under the graph of the function has different interpretations depending on the what the function represents. In fact, the technique was developed for finding areas, will also enable us to compute the volume of a solid, the length of a curve, the force of water against a dam, the mass of the center of the mass and the center of mass of a rod. That actually is in Calc 3. The work done in pumping water out of a tank and the amount of fuel needed to send a rocket into orbit. So they tell you that there's some things that the area of the curve is going to tell you. Every now and then students will go on and they will tell me, oh, we were doing that, finding the area under the curve or finding the integral, finding the derivative or whatever have you. And one of my students who's a med student was saying that in their pharmaceutical class that they were doing the integrals to find how long it took for your liver to process a drug like aspirin or Tylenol or whatever have you through your body. Anyway, kind of interesting. So we start off just on how we would estimate the area under the graph. And just a simplistic way, there's other ways about it as well, but a simplistic way is to, because the area of a rectangle, is to use a rectangle. And so they have their curve here, and they're saying if they use left endpoints. So you notice that this rectangle has a left side and a right side, and the curve, getting my L out here on my hand, right? The left side. So this one is a left endpoint. And so because the curve is hitting the left edge of the rectangle and the left edge of the rectangle and the left edge of the rectangle and the left edge of the rectangle. You can use different size rectangles, or you can use the same size rectangle. It's obviously easier if you use the same size rectangle. You could see that it does estimate the area under the curve, but a little wee bit is left out right there. And if you use the right endpoint, now this rectangle has a left side and a right side, and the right side is hitting the curve. The right corner of the rectangle is hitting the curve, etc. And you can see that, hey, it gets the entire amount, and it's a wee bit too big. Now curves this curve is continually increasing, right? And this curve, same curve, continually increasing. And so the left is a little too little and the right is a little too big. You might say, hey, why don't you find this and find that and average it? Hey, that's be something that someone could do, right? And the other way is to use the midpoint. And now the very middle of the rectangle is hitting my curve. You could do a variety of these things. But just to make it simple and have the idea, they ask you just to do one thing and not put too many things together. But that's, and the other thing that you could do, I mean, it's possible if you wanted to get really on finding it, is that you could go, that's a little, looks like a little triangle. You could go and find the area of those triangles. Okay. So you could get crazy, was what I'm saying. But we're trying to estimate the area under this curve. The curve is here, and it goes, and when they talk about the curve, they're saying all the way the area to the x-axis. So the area under the curve that's trapped by the curve and the x-axis. So we're going to look at, this is problem 4 out of your textbook, and it says estimate the area under the graph f at x equals sine of x from 0 to pi over 2 using 4 rectangles. And then it said use right endpoints. Sketch the graph and the rectangles. If the upper bound is b and the lower bound is a, and n is the number of rectangles, then the width of each rectangle was given by this formula. The width of each rectangle is called delta x, and it's b minus a divided by n. So in our case, they were telling us to go from a, x equals 0, to b, x equals pi over 2. So this would be pi over 2 minus 0 divided by n, and n is the number of rectangles. And they said on this particular example for us to use n is 4, is what they asked us to do. So I'm going to put 4 in here. And so when I do that arithmetic and the dust clears, I get pi over 8. And you can do that on your calculator if you need to or want to. I did get a calculator here, and so that I could put things in. So my fraction, I need another fraction. I need pi over 2 minus 0. So you literally could put the whole thing in if you wanted. Divided by 4, when I hit equals, I do get pi over 8, or 1/8 pi is the same as pi over 8. Okay, so I'm going to be starting, and I'm going to just write these out here just so that you know what I'm doing, and I could see where a person could do them in their head. So I want to make sure my calculator is in radians. It is in radians. So I want to find, I'm starting at 0, so I want to find f at 0. And if you wanted to write it like this, you could, or you could write it in a little table, your choice. I think this time I'll write it like this. So f at 0 equals the sine of 0, and the sine of 0 is equal to 0. And you can use your calculator to verify that that's true. And then f at pi over 8, and the sine of pi over 8 isn't one that I know. Let's see what our calculator says about it, just for curiosity purposes. So the width of our rectangles are pi over 8, so I'm going to be going by pi over 8 here. So sine and then pi over 8. And let's see what this calculator says about the sine of pi over 8. It says, ooh, it's a decimal. Okay, so I'm just going to leave it as pi over 8. Then I'm going to go, so the width of each rectangle, so here's the, I'm going to just draw this here. Maybe I'll draw it in purple. So there's the bottom of my rectangle on the x-axis, and the width is pi over 8. So that's the first rectangle. The second rectangle would go from pi over 8 to pi over 4, which is also a width of pi over 8. So I'm going to find f of pi over 4. I think f of pi over 4 is one I know, right? Because I think I know the sine of pi over 4. I think it's a friend. I think it might be the square root of 2 over 2. I think it's okay to give it a whirl on your own and then use your calculator to verify. I think that actually helps you get them all memorized. And I do think that that is the way to go on them. So good guess on my part. Then the next rectangle goes from pi over 4 to 3 pi over 8, and that's a width of pi over 8. If you were like, well, can you show me that that's a width of pi over 8? Well, if I started at pi over 4, so pi over 4, and I added pi over 8, I do get 3 pi over 8. And so these widths are out here. The next one is going to end at pi over 2. So from 3 pi over 4 to pi over 2. Should it go exact? I just didn't know how to cut that off. I do now, but I didn't then. And so anyway, so we're finding all of these. So f at pi over 3 pi over 8 is sine of 3 pi over 8. And the last one, f at pi over 2 equals the sine of pi over 2, which I think the sine of pi over 2 is equal to 1, if I'm not mistaken. Okay, so I kind of have these listed out. Now they told me to use right endpoints. So for this rectangle right here that has a base that goes from 0 to pi over 8, the left endpoint is at 0 and the right endpoint is at pi over 8. So they want me to use the height that we got for pi over 8, which was sine of pi over 8. So I'm going to go up here and I'm going to draw right here. That's the right. And I'm going to draw this rectangle that would be in here. And this rectangle goes from, so I'm trying to estimate the area under this curve right there. And I've got this rectangle that looks way bigger, right there. This is just to give you the idea you would make your rectangle smaller. And so I'm going to be using this rectangle that has a height of sine of pi over 8, which we figured out was a decimal value. Okay, so then for the next one, I'm going to draw the next rectangle, and the next rectangle goes from pi over 8 to pi over 4. This is the bottom of the rectangle on the x-axis. And this now, the pi over 8 is now the left of this rectangle, and the right side of this rectangle is pi over 4. So I want to use the height of the rectangle, which will be square root of 2 over 2. So that came out nice. Or you could call it sine of pi over 4. Doesn't really matter right now. So this is the height of this rectangle. And I'm going to draw this over here straight across. For the whole rectangle has the same height, right? And I know that it's a big rectangle. And yeah, to make it more accurate, I would make smaller rectangles. But if I made smaller rectangle, I'm going to label this square root of 2 over 2 as the height. But if I made smaller rectangles, it wouldn't be, you wouldn't be able to see kind of what's going on. So I'm trying to estimate, so that's the reason they ask us with these big rectangles. I'm trying to estimate the area under this curve right here. That's my idea. And I am using this entire rectangle to estimate that area under the curve. This entire rectangle here. And so, this entire rectangle is going to be what I'm going to use to estimate the area under this curve. And then the next one, the next rectangle goes from pi over 4 to 3 pi over 8. And the height that we want to use, so this is the left-hand side of this rectangle, and this is the right-hand side of this rectangle. So I'm supposed to use the height for this rectangle to be 3 pi over 8, which wasn't a nice value. So I'm going to draw this rectangle in here, and I'm going to draw this height right here on the right-hand side. And I know that height is sine of 3 pi over 8. And I'm estimating the area under the curve to the x-axis, and I'm using this rectangle here that has a height of 3 pi over 8. The reason I'm using the rectangle to estimate the area under the curve is I know the area of a rectangle. The last rectangle goes from 3 pi over 8 to pi over 2. And I'm supposed to use, this is now, for this rectangle that goes from 3 pi over 8 to pi over 2, right? That's the bottom of the rectangle. 3 pi over 8 represents the left-hand side. The right-hand side is represented by pi over 2. So that's what I want to use for the height of this rectangle. And that height is equal to 1. So I'm estimating this area under the curve, right? And I'm using this whole rectangle to estimate that area. Okay. So now I'm going to write out what I have here. So I have 4 rectangles right here, and the area of each one of those rectangles is the base times the height. And the base is how wide it is. And we know that all of them had a width of pi over 8. So the first rectangle right there, you'll see in your book that they might even write A equals, this is the area, and that they're trying to approximate, equals rectangle 1 plus rectangle 2 plus rectangle 3 plus rectangle 4. And you can even use the squiggly equals, since the area that I'm kind of referring to is the area under the curve, and I'm approximating it with these rectangles. This first rectangle, this one right here, is R1. That's my first rectangle, and it had a width of pi over 8, and it had a height of sine of pi over 8. The second rectangle, this rectangle right here, rectangle number 2, it had a width of pi over 8, just finding the area of a rectangle. Remember, so for each rectangle, the area is width times length, and in this case, width times height, I'll say. And so that's the area of each rectangle. Each one of these rectangles has a width of pi over 8, and they have varying heights. So this rectangle had a height of pi over the square root of 2 over 2. And the next rectangle, rectangle 3, that's this rectangle right here. The width of pi over 8 times the height, which is sine of 3 pi over 8. And then plus at the very last rectangle, rectangle 4, pi over 8 times the height of that rectangle, which I didn't label on here, but I'm going to label right now, which is 1, right? And which was sine of pi over 2, which is 1. So this is what my area is going to be approximately equal to. So I'm just going to put that in my calculator and hit equals. And they wanted to know, after I used this to find the estimate, and remember this ended here, but I didn't know at the time how to stop drawing it there on Desmos. I know now, and so you don't have to send me an email on how to do it. But I drew the graph for you. They had you drawing the graph in the book just to make it a little bit faster, and on our first problem. Okay, so I'm going to be putting this in the calculator. Do you notice that they all have pi over 8 as the coefficient? And so you could factor out a pi over 8, and why that would be helpful is putting it in the calculator, right? So you could factor out the width, which was pi over 8, and you could say then I need to add sine of pi over 8 plus the square root of 2 over 2 plus sine of 3 pi over 8 plus 1. And so I think I will do that just to save some effort in my calculator. If that wasn't pi over 8 and wasn't kind of hard to put in the calculator, I think I wouldn't have bothered. I would have just went for it. So here's my pi over 8. And so I'm putting that in, and then I'm going to use parentheses. And then sine, my calculator is in radians, of pi over 8 over 8. And I'm going to close those parentheses, and I want to add the square root of 2, which is fraction as well, the square root of 2 over 2, plus the next one, which is sine of 3 pi, sine of, make the fraction, 3 pi over 8. Close those parentheses, and then plus 1. And close the parentheses because that'll be all times pi over 8 that we had on the front. I hit equals, and the calculator says this is approximately, and they would need to tell me where to round. I don't know that they have told me where to round on this problem. 1.1834 6, 5. I don't know where they said to round on it. I did bring my my other computer here so that I could look in the back of the book, and maybe I've missed. Did you read carefully and see if it told me where to round on this area? And they went 4 places, so I'll just follow them is what I will do. And I would let you know where you needed to round to. And I guess this problem didn't. Maybe it did, and I just didn't get it typed. So 4 places, 1, 2, 3, 4. The next place was a 6, so we would bump up here. This problem was part A. Part B was to do the same thing, but instead of using the right endpoint, to use the left endpoint. So we would have a rectangle here that has a height of 0 if we did that. And then the next one would have a height of sine of pi over 8, etc. And then the part C asked you to use the midpoint. So the midpoint would be right here, and you would need to go and find what the midpoint is, and then what the height is, and then you would be drawing your rectangle in there, and etc. along the way. I'm not going to do that, but if you want to go and do that, you can. I have got the answers up on Canvas, and you can check it out and see what answer you get. They asked me, hey, was this an overestimate or an underestimate? And you can see that my rectangles are bigger. Little bit go over the top of the area, right? I was trying to estimate this area from this curve to here, and every single one of my rectangles are a little bit too big, and so mine is an overestimate. Sometimes one rectangle's too big, and then the next if the curve goes up and down, and the next rectangle's too small, and etc. That can happen. And it's hard to know whether it's an overestimate or an underestimate. But they asked you on this problem because it was really obvious what it was. Okay, so this is problem 5 in your book. And so it says, estimate the area under the graph f at x equals 1 plus x squared from -1 to 2 using 6 rectangles and left endpoints. Sketch the curve and the approximating rectangle. So we're going to have to do the whole thing here. And so what I like to do first is find delta x. So delta x equals b minus a divided by n. So it's a little bit of a formula. Right here is a. Right here is b. And n is 6. Okay, so this is going to look like, let's see, b is 2 minus -1, that was a, divided by n, which was 6. So this is 3 over 6, which is half. So each rectangle is going to be a half wide, and so I'm going to make a little chart here. And so I'm going to call this, instead of f at x, I'm going to call it y in my little chart. xy. And I want to start at -1. And I want to go up by half. So you can use your calculator or you can use your head. So if I start here at -1 and I want to go up by half because that was the width, so up by 0.5, you could put in half if you wanted as well. and I get negative 1/2. And I want to go up by half. So if I add half to that, I get 0. I want to go up by half. So if I add half to that, I get half. I want to go up by half. So if I add half to that, I get 1. And I add half to that, I get 1.5. And if I add half to that, I get 2. And I want to stop at 2 because that's where it said to go to. And then I'm going to use my calculator or my head, and I'm going to be putting this into my calculator. So what I'm going to be putting in, I have y equals 1 plus x squared, right? And I'm going to be plugging in, right? I put a parenthesis where I have x squared. I'm going to be plugging in right here, negative 1. And you can do it on your calculator or in your head. It doesn't matter. And since I'm going to be doing it repeatedly, I think I will just go ahead and put it in my calculator. So the first one I have negative 1, and then quantity squared because I can just keep editing this. And so when I do that, I got 2. You probably knew that. Now I'm going to change that 1 in my calculator to negative half. So I'm going to put in here fraction 1/2. And I'm going to get 5/4. And then I'm going to change that to 0. Hey, I'm going to just edit out the negative and do the 1/2 while I'm here. Oh, that's 5/4 as well. Yeah, that I should know that, huh? And then 0, well, I could do 0 in my head too, probably. That's 1, saving a little time. Negative 1 and 1 should be the same. And we found that negative 1 was 2, so this is 2. Now, when you go to put 1.5 in your calculator, if you think that you can just go over here and put the 1 right there, that seems like it looks like 1.5, you can't. So I did do that, but I want you to know that it's thinking that I'm doing 1 times 1/2. So even though that's not what it looks like on the calculator screen, but that's what the calculator thinks I'm doing. So if you want to put it in as a mixed number, what you have to do is you have to hit the shift and then this key right here, shift and then that key, and then now I can put in 1.5. And it will do it correctly, 13/4. So the way that I was about to do it, it would not have done it correctly. You're saying, well, you didn't show me that it wouldn't do it correctly, but I will show you that it doesn't do it correctly. So if you had the half here like that, and then you just came over here and you put a 1 and you hit equals, it thinks that you're doing 1 times 1/2, so that it doesn't realize that. Now I want you to also know that, of course, 1.5 is 1.5, so you could have done that as well. So you could have put in here 1.5 and done it, but people will have trouble with their calculator, so I just wanted to make sure, since I had the opportunity to show you what I was putting in, that, hey, there's different ways of going. Now I want to put in 2, so when I put in 2, 2 squared is 4, plus 1 is 5. Okay, so that it's asking me to sketch the curve and the approximating rectangles. I'm going to use this both to sketch the curve and the rectangles. And so we're going to start here, just kind of looking at the size. 13/4 is 3.25, and the highest one I have goes up to 5. And I had none that were negative, right? So just as I just try to draw my little rectangles and leave myself some room here as well. So I'm going to be over here at -1, and then -1/2, and then 0, which is the y-axis right there, and then at 1/2. So the best of my ability, I'm drawing these equally sized. You don't have to be perfect. I'm going to label that one 1.5 and 2. So to the best of my ability, I drew my, on my x-axis, half width there, and then a height of 2. Remember, I was going up to a height of 5. So I'm going to make this height of 1, height of 2, height of 3, height of 4, height of 5 is what I'm going to have. So at -1, I was at a height of 2. And at half, I was at 1 1/4. 5/4, that's 1 1/4, right? And then at 0, I was at a height of um, 1 1/4. That I made that at 2 1/4. Sorry, 1 1/4. And at 0, I was at a height of 1. At half, I was at a height of 5/4, which is 1 1/4 again. And at 1, I was at a height of 2. Yeah, it'd have been better if I had grid paper here. At 1 1/2, but it's okay. It's just a sketch. So at 1 1/2, I was at 3.25. So here's 3. So I'm kind of making a little line here. 3 and 0.25. And at 2, I was all the way up at 5. Okay. So here is my curve. Now I'm going to draw, and the area they're trying to get me to find, to estimate, is this area here, underneath the curve and trapped by, so here is the area that they're trying to get me to estimate, right there. So that's the area that they're trying to get me to estimate. And I'm going to be using these rectangles. And they said for me to use the left endpoint. So this is the left, this is the right. Is that okay for this first rectangle that goes from -1 to -1/2? So there's the base of the rectangle right there. And I'm going to use the right as the height of it. So this is, the left as the height of it. And so the left endpoint. So that's going to be the height of the rectangle. So I'm just going to go parallel to the x-axis straight across to make a rectangle there, and then down here. So there's my first rectangle, and the height of that first rectangle was 2. So I'm going to put a 2 up there just so I know. Then I'm going to draw my second rectangle. I'm going to erase these lefts and rights here. And so for my second rectangle, the base goes from -1/2 to 0. So there's the base of the rectangle. And I'm supposed to use the left side as the height. And the left side was 1 1/4 or 5/4. So straight across here. And that's going to be this rectangle 5/4. So that you can see that these rectangles, the 2 rectangles I got so far, are not quite big enough. Okay, and then the next rectangle is going to go from 0 to 1/2. And I'm going to use, so from 0 to 1/2, and I'm going to use the left as the rectangle's height, which is a little bit, I said not big enough, and I meant a little bit too big. Sorry, there's a little bit more. I'm going to find a little bit more area than the area under the curve. I'm going to find a little bit more area than the area under the curve. This one is not quite big enough, right? There's a little bit of area above here that I'm not going to be counting. Okay, then the next one goes from 1/2 to 1, and I'm going to use the height of 1/2, which was 5/4. So I'm going to draw this across here. 5/4 is the height here. And there's my rectangle there. And you can see that that one's not quite big enough either. And so they're not going to be perfect. Couldn't you use other shapes other than rectangles? And yes, in Calc 1, we practice with rectangles, but yeah, you can use other shapes as well to estimate the area under the curve. So you can let your imagination flow, and believe you me, people have done that. But this simple, just using these rectangles is what we're looking at now. And so let me see here, friends. I need to do the next rectangle, which is from 1 to 1.5. I'm going to use the left, which is 1 for that rectangle, and that's a height of 2. And then the last one goes from 1.5 to 2. That's the base of the rectangle, and it has a height of 3.25. So this is its height, using the left as the height. Okay. So they asked me to estimate the area under the graph using 6 rectangles. So you notice I got 6 rectangles here. 1, 2, 3, 4, 5, 6. And I use left endpoints for all of them. I've sketched the curve. I've got the approximating rectangles all sketched, right? So this is the rectangle that I'm going to be using. And this rectangle here, which the rectangle is just a little bit too big. This rectangle a little bit too small, a little bit too small on this one, a little bit too small on this one, but there's my rectangle. And here's my rectangle there. Okay, so I'm going to say that the area is approximately equal to, and I'm going to use that trick that we used before of, I know that it is, this rectangle is half times 2, and this one's half, which is its width, times 5/4, and half times 1. But because they're all the same size, I'm going to factor out the half, and so times 2 plus 5/4 plus, hey Susie, what are you doing, girl? Are you going to come on camera? Are you going to come on camera and show everybody you? Is that what you're wanting to do, or are you just going to put your tail for them? Here. You got to see Susie. And so how do I go back to person view? See, there's Susie. And so how do I go back to paper view? She got right in the middle of our problem. And so I was adding these up, 2 and 3.25. So this is going to be my area right here. So 1/2, 0.5, I'm going to put instead. And 2 plus 5/4. I'm going to do 5 divided by 4 plus 1 plus 5 divided by 4 plus 2 plus 3.25. I forgot to end the parenthesis. I wonder if that makes any difference. I'll put it there. And then, no, it didn't. Okay, so I'm getting 43/8. And they didn't tell me where to round here. And so it doesn't really come out that bad. I think they took 4 places on the other one, right? Okay, so we did a lovely job on that one. So I have another one to do here. They ask you on the same problem, I believe in the book. I had my book here. Where did I set it? It's over there. I'm not going to look at it. If I'm not wrong, you can look and you can tell me if I'm right or wrong. That I think they might ask you to also do right endpoints and maybe the midpoint. I'm trying to just do one of each and not, chug through it. I don't think that you have to practice a million of these to get the idea of it. And they're a little bit tedious, as you can kind of see. Okay, so here is asking me to estimate the area under the graph from 1 over x from 1 to 2 using 4 rectangles and left endpoints and left midpoints. I have obviously had a typo. I want midpoints is what I wanted here, so I'm going to make a note for the real students next semester so that I fix that typo. But midpoints is what I was wanting on my example here. And they do ask for midpoints in your book, but I wanted to have another one to draw is what I wanted to do because that's the part people have trouble with. Okay, so the first thing that I usually do when they want me to do that is I find the width of each rectangle, and there's a formula for it, b minus a divided by n. And this case, our a is 1, and our b is 2. 2 minus 1 divided by n. They said 4 rectangles, so they're saying that n is 4. So each rectangle is going to be 1/4 big, right? And so small. Then what I usually like to do on these is I like to make my table right here. And if they call this f at x, I like to call it y. And I want to start at 1, and I'm going to end at 2, and I'm going to be going up by 1/4. So the next one would be at 1.25. I'm just going to allow myself to go in decimal. The next one would be at 1.5, and the next one would be at 1.75, going up by 1/4, and then the next one would be at 2. Oh, I wanted midpoints. We're going to have to talk about that. And so I had forgotten I wanted the midpoint. And so I'm going to come here and I'm going to erase this, and I'm going to leave a spot in between on all of these. So this is 1.25. I had forgotten I wanted midpoints. So the next one, when I add 1.5, I'm leaving a spot in between, for the midpoint. 1.75, a spot in between for the midpoint, and then 2. Now it's my choice. I mean, I'm going to have a lot of points on this curve to graph it, and I really don't need that many points on the curve to get a drawing of it. This is one of my 6 basic graphs, and I kind of already know what it looks like. So I certainly don't need 1, 2, 3, 4, 5, 6, 7, 8, 9 points. But I have listed them out like this. I didn't make the mistake on purpose, but I hope that making the mistake actually points out that what I kind of need going on there. And so I'm going to really be interested in the midpoint. So between 1 and 1.25, I want the middle of that. And a way that you could find the middle of that is you can find the average of that. So you could add 1, find the average, you add them up and divide by 2. 1 plus 1.25, and then divide by 2. And that gives me 9 over 8, or 1.125 in the middle. Oh man, I made this problem up myself, and the numbers are not that nice. That's 1 1/8, right? I don't know. Am I going to be able to fit that there? So that's really what I'm interested in. And then if you want to find the next one, they should all be 1/4 away from each other. So I could just now add 0.25, right? And so plus 0.25 to find the next one. 11 over 8. Maybe I would be happier with fractions. 11 over 8. I think I will be happier with fractions. What was this one as a fraction? I'm not happy with my numbers, though. Did that ever happen to you? Okay, 9 over 8. It's going to be easier as fractions. Okay, and then the next one that I want to be paying attention to, I think, will be 13 over 8. I'm just guessing, though. So 11 over 8 plus 1/4. Because that's how far apart. Yeah, 13 over 8. At this point in my existence as human beings, I wish I would have made the little spot a little bigger. Plus 0.25. The next one, which I think will be 15 over 8. Okay, so those are the ones I'm really interested in, because I'm really interested in the midpoints. And I'm going to put them in my into my to find the y value of them. I can also find the y value on these if I want, and I only do those if I need them. And so when I put in, and so this is what I'm going to be putting in the calculator, right? Y equals 1 over, and then I'm going to be putting in 9 over 8 right here, 9 over 8. And when I do that, I get, it just does the reciprocal of it. So that's kind of nice. And so I get 8/9. And it just does the reciprocal. So I get 8/11. So I could put it in my calculator. The next one should be 8/13. And the next one should be 8/15. So I'm going to go and I'm going to draw this to the best of my ability. So I need from 1 to 2. I just want to show you what this sketch should look like. So y equals 1 over x. This is just from memory. It should look like this. It's a hyperbola, and it's got 2 branches, but I'm in just from 1 to 2. So here's 1 and here's 2. And so it's just this little curve right there is all that I'm having, but I'm going to blow it up bigger just so that you could see, because it said to sketch the curve. Now, when they say for me to sketch the curve, I only have to sketch the curve from 1 to 2. And so I'm going to come right here, and just like I did on that one, and here's going to be my axis right here, and I'm going to have 1 right here, and I'm going to have, I'm going to go over here and I'm going to put 2. And then I'm going to have a rectangle that goes from 1 to 1.25. And so I'm going to draw that on here. Maybe I should just draw those on there to begin with. So here's my next rectangle, 1 to 1.25. The next rectangle, 1 to 1.5. I tried to make those the same distance. And I'm not being a perfectionist. I'm just trying to make it a little more perfect. And so, so here's 1, here's 0.25. I guess I have a little break in the graph because I definitely am not doing the same distance from 1 to 2, right? So, and then the next one, 1.75. Thank goodness they didn't ask me to go all the way to 18 or something awful like that. Okay, and then 9/8 is in the middle of that rectangle right here, and it has a height of 8/9. And all I'm going to do to kind of sketch this thing in here is I'm going to go right here and I'm going to put in 1, which was my end point, and I'm going to put in 2, which will be half. So you're going to see some cheating big time here on getting this sketched. And so I'm kind of glad. I mean, sometimes I make a problem and I'm like, oh, these numbers are just exhausting. And they actually use the word exhausting in finding these in the book. So if you go read the textbook at the beginning of the book, chapter 1, and you read about the area problem, there's the method of finding the area, estimating the area by exhaustion. Now, I'm only finding 4 rectangles, so it shouldn't be that exhausting. So right here at, oh, I didn't, the height wasn't the height wasn't 2, the height was 1/2. Sorry, friends. I don't know. I was talking, not on the phone though. And so right here, this is going to be 1 and this is going to be 1/2. Okay. So I'm going to come up here and I'm going to put 1, 1 on here. And I'm going to put, just making my little curve here, 2. And I'm just going to draw, remember what the curve looked like. That's what the curve looks like. So just to the best of my ability, I'm just going to kind of draw in here. The curve kind of come in here, like that. Okay, so now I've got the curve drawn there. All I use to draw the curve is basically what does it look like and the endpoints. Now I'm going to put the rectangles on there, right? And I'm going to go right to the middle of this rectangle. And I'm going to go straight up to where it hits the curve, and I know that that height must be 8/9, right? Because that's that first rectangle. And I'm going to go both ways. I'm going to draw straight up here and straight up here, and this is going to be the height of the whole rectangle. So doing the midpoint is a little harder for me to get drawing on it, particularly these numbers were not that great. Okay, then I'm going to go to the middle of this rectangle, the one that goes from 1.25 to 0.5, and I'm going to be here at 11/8 in the center of that rectangle, and 8/11 is how tall it is, but I know that should also be the same height as the curve. So this is 8/11. Then I'm going to draw this straight across here. And that should look like it's right in the middle of that rectangle to the best of my ability, right? Okay, then, and it has, that whole rectangle has a height of 8/11. The next rectangle that goes from 1.5 to 1.75, this is going to be our third rectangle. And the height is right in the middle at 13/8. So right here in the middle, I'm in the middle of that rectangle. And I'm going to use this as the height. And we said that that height was 8/13. So 8/13, I'm going to label it. And then I'm going to draw parallel to the x-axis, best I can, that rectangle in there. And there's that rectangle. One more rectangle to do. It's the rectangle that has the base that goes from 1.75 to 2, right? And so 1.75 to 2, and it's going to have a height of 8 over 15 right in the middle of the rectangle. Do I have to go and label those spots? And the answer is, if it was convenient and you wanted to, great. And if it's not too convenient and you don't want to, this one's almost flat there. And so at 8 over 15. Now I have the curve drawn, and I have if they were better numbers, I would have labeled out all those numbers like I did here on this one to draw it. But I was like, nope, I'm going to have to use what it looks like and then just kind of say that my stuff matches it. And you see that I'm using the middle of each rectangle. So the area, using that same idea that I can factor out, they all have a width of 1/4. So I can factor out the 1/4. So this is approximately equal to, I don't get crazy if you put equals or approximately equal to, but I like the squiggly equals to show that it's approximately equal to the area under the curve. And that is 8 over 9 plus 8 over 11 plus 8 over 15 plus 8 over 9, 8 over 11, 8 over 13. I missed 8 over 13. Plus 8 over 15. And so I'm going to find that area. This is what I'm approximating that area to be. So 0.25 times, and then 8 divided by 9. I could put it in fraction mode in my calculator, but I was feeling lazy. So I certainly could have done that, though, like that if I would have wanted. Plus 8 divided by 11, but this is the same, so I'm going to do that because it's faster. 8 divided by 13 plus 8 over 15. In that parenthesis, hit equals, and I get that big value right there, which I'm sure that since they're having me approximate this, that they had probably took in the back of your book to 4 places like they did on the other. So this is 0.69121. 4 places would be that area. So 1, 2, 3, 4 would just be a 2. Great. Okay, so this is just one, and I think it's our last example that we have. But they're telling us here, if the velocity is 30 miles an hour, find the distance traveled or the displacement in 2 hours. And they just wanted me to draw it just so that you could kind of see. So this velocity curve that we have right here is constant. And so it's a little bit silly, but I am going to go ahead and I'm going to draw it right here. So this is going to be my velocity curve. This is going to be 30 right here. And this is 0. This is 1 hour. This is 2 hours here, right? And so this is just like this. And they're wanting me to find the area under the velocity curve because how come I can't draw that looking parallel to my x-axis? I couldn't do it, but I was trying to. So there's 30 on my velocity curve. This is time, which is in hours. This is my velocity, which is in 30 miles per hour. So if I find the area under this curve, well, it's exactly a rectangle. And so that area right here is 30 times 2, which is 60, right? It was 30 miles per hour. I'm going to write this out. Miles per hour times 2 hours. The hours cancel out and gives me 60 miles. And they were just wanting you to see that, hey, that goes exactly with our formula for distance. It's rate times time, right? And our rate was 30 miles per hour times 2 hours, which the hours cancel out and gives 60 miles. And so certainly that was true. Now, and if I was trying to find the distance and I traveled a constant speed, then this is what I would do. But you don't travel a constant speed. Even if you are able to, even if you're on a racetrack, if you start at zero, right? I mean, the only way that you would be doing a constant speed is if you were able to get up to speed and then just go straight. Because even if you hit a corner, you're gonna have to slow down a little bit, maybe for that corner or whatever have you. Okay, so anyway, so they're gonna have us do one that. So this is unrealistic, really. But I guess if you got on the open freeway, well, people would be honking at you at 30 miles an hour. Okay, so the table shows the speedometer readings at 10-second intervals during a 1 minute period for a car racing at Daytona International Speedway in Florida. And part A asked us to estimate the distance the race car travels during the time period using velocities at the beginning of each time interval. And so you could draw a picture of this if that was helpful to you. And so we kind of have here at 0 and at 10 and at 20 and at 30 and at 40 and at 50 and at 60. And if they're saying to use at the beginning of each time interval, so for the first time interval, this would be my, I'm looking at my estimated using these rectangles, like the area under the curve. So I would use the height for 0. I would use that as the height for my velocity. So if I'm trying to make my graph, this is my time right here, right? And then this would be my, going over here would be my velocity. And I would go up, 182.9, and I would draw here a point at 182.9. And yeah, that's not exact, of course, but just to give you an idea. And I would use then that height for this entire 10-second, even though the race car slowed down a bit. 168 miles an hour is a little bit less than 182. This is not to scale, friends, right? But I would use, because it said for the whole entire time interval, to use the height of the beginning, which was 0. And I would continue like that. Now, if I'm trying to estimate the distance, you notice that I have a mismatch in my units. This is in seconds, and this is in hours. And so my choice is to turn all of these into all of those into like maybe feet per second for your velocities, and they sometimes do that, or to turn all of the time over here into hours. That would be my choice. And on this particular one, what they did in your book is they turned the time into hours. I went and looked because I just kind of wanted to follow them. And I know that there's another problem when they go and they turn everything into feet per second. And so either way is good. And so if I wanted to, and you should get the same answer, I guess is the point. So if I turned the 10 seconds into hours that we're having each time here, then let's see here, 10 seconds, S for seconds. I'm going to write this over 1. And I know that 1 hour equals, do you know how many seconds there are in an hour? And so I know that there's 60 seconds in a minute, and there are 60 minutes in an hour. And so that means there's 60 times 60, which is, I spilled some tea there, so I was embarrassed and covered it up. 300 and 3,600 seconds in an hour. So this right here, when I cancel out the seconds and I reduce this, I get 1 over 360th of an hour, right? Is that okay? And so that's what the width of each of these is, because they're all 10 seconds. And so they said for the first 10 seconds to use 182.9. For the next one, that's going to go from 10 to 20 seconds, they want me to use 168 as the whole entire height, because you use what's at the beginning of the time interval. So from 20 to 30 seconds, I'm going to be using 106. So that's even smaller. Does it really matter on the scale? And the answer is no, it doesn't. They didn't ask me to draw this, so it doesn't have to be perfect. I'm drawing it for me. From 30 to 40, I'm going to use 30, which is 99.8. And from 40 to 50, I'm going to use the beginning of the time interval, which is 40, which is 124. So that's back up here. Not drawing it perfectly again. 0.5. And then the last time interval, I'm going to use the race car's speed of 176.1. So 176.1 is precisely here. Yeah, no, it's not really precisely there. Just giving you the idea. So 176.1. And so if I want to know the distance traveled, because the race car went straight, it would be this equal to the displacement in this case, because the race car just went straight down the track. I think, did they say that? They're acting like it's going straight down the, I don't know what Daytona is, curved track, but we'll say that it's going kind of like it's going straight down the track, which is equal to the area that I have right here. So I want the area of this rectangle, the area of this rectangle, the area of this one, the area of this one. And remember that the area is how wide it is, which I said was 1 over 360 of an hour, times how tall it is, which is 182.9 miles per hour. So this is going to look like each piece is going to be 1 over 360 of an hour. I'm going to put the units on it, multiplied by 182.9 miles per hour, plus, and then the next one, 101 over 360 hour, times, and then 168 miles per hour. So that when these cancel, right, I'm going to get, and I multiply these together, I'm going to get a very small number of miles. And here too, the hours cancel, and I'm going to get some miles. And I'm going to continue doing that for all 1, 2, 3, 4, 5, 6 rectangles. So what I'm going to be putting in my calculator, and this will be miles plus miles plus miles, and I'll add them all together, and that'll be how many miles that this race car traveled in 10 seconds is what it will be. So I'm going to write it like this in my calculator, 1 over 360. And then I'm going to factor out the 1 over 360, and then 182.9 plus 168 plus 106.6 plus 99.8 plus 124.5 plus 176.1. And that's what I'm going to be putting in my calculator. And this is going to be really an estimate, so I'm going to do squiggly equals. Okay, so I'm going to do the fraction. Boy, it's kind of cold in my house. 360. I'm going to eat some breakfast too after this video. I'm not even kidding you. Um, while I'm loading it onto YouTube. Okay, provided I didn't make any typing errors as I put it in. If I did, you're probably shouting at your screen. I hope I hope you have your calculator out too, and are putting it in. So I'm getting 2.383. They took 4 places, so I'm going to do 4 places like they did. They took 4 places on the one that I looked up at the beginning, right? And so miles, and so more than 2 miles, less than 2.5 miles. I have my it probably has crashed. No, it didn't. Lucky me. So I have my computer, and I was able to put the answers back up on Canvas. Ooh, I shouldn't say that because they might make me take them down again, and then you'll say they're not there. Okay, so yeah, so that is what they gave for the. They actually rounded to 3 places, and not 4 on this one. But okay, so this is what they're giving. I do want to show you how to turn this into feet. And the reason I want to show you how to turn it into feet is because I know that there's a problem on the lab that asks you to do that. And so, so you could do the problem just like what we just did here. And then we know, so if you wanted to turn this into feet, we know that 5,280 feet equal 1 mile. So I know that they didn't ask you to do this on this problem, but I want to show you how to do it. So the answer in feet would be, so you would take your 2.2, no, that's 2.3, 3831 miles, and I like to write it over 1, and I would times it by, now I want miles in the denominator, 1 mile in the denominator, so that the miles cancel out, and 5,280 feet, 5,280 feet equal 1 mile in the numerator. So this will convert this into feet when I just multiply those together. So this would be 2.3831 times 5,280, which is I got 768 here, but if I was doing feet, you probably would be rounding just to the nearest foot. So 12,000 is an estimate after all, feet, right? So, 12,500 feet, and is how far this went. So this was what they were wanting. This is what they have in the back of the book. I admit it, but I know that I asked you to do one and asked you in feet. So this is how you could convert it to feet. So it's not very hard to convert it to feet, I guess is what I'm saying. If you needed to. Now here they're asking me to find the lower estimate for the distance traveled by the race car. And so this is part C. And so you notice here that when I use 0 for this time interval. And I used for the next time interval 10 and next time interval 20 and 30. So you might be wondering, is this estimate down here, this estimate, is it an overestimate or an underestimate of what the number of feet that the car really went, or the number of miles that the car really went? Well, from this time interval, from here, it was slowing down, and the car was slowing down. So in that, because it started off going 182.9 miles an hour, and at the end of the time interval, it was going 168 miles an hour. So, using 182.9 for this whole time interval was an overestimate of how far the car went in that 10 seconds. Because it was slowing down. In the next time interval, from 10 seconds to 20 seconds, the the car slowed down even more. So using 168 was another overestimate. But in this time interval from 30 to 40, the car was speeding up. It was going 99.8, and then at the end of the time interval was going 124.5. And so maybe it hit a corner here, and that's why it was slowing down. I'm not sure. And now it's going on the straightaway and speeding back up. But this is an underestimate of how far the car went if we use 99.8 for it. So now they're wanting me to do a total underestimate. That's what they're wanting me to do here. And so what I'm going to do a total underestimate is between each time interval, you want to use the smallest is what you want to do. So from 0 to 10, you want to use whichever one of those is the very smallest, which 168 is the very smallest. Okay. And then the next one, which goes from 10 to 20, I want to use the smallest. So between 168 and 106.6. So I want to use the smallest, so I'm going to use 106.6. Then in the next time interval, I want to use the smallest. So between 20 and 30, I want to use the smallest, which was 99.8. So between the next one, I want to use the smallest. Between 30 and 40, I want to use the smallest, is what I want to use. And so you notice that I'm going to use the smallest for the next time interval between these two, and the smallest is 99.8. So I'm going to be using that one twice. And so when I go to draw this over here, because I'm going to have to keep flipping back and forth, that's the reason I was on there drawing it like that. So 0 and 10, but then I don't want to confuse you, 30 and 40 and 50 and 60. So we said between 10, 0 and 1, I had to use the smallest, which was 168. So right here, and that was the height that went with 10, but 168 is what I'm going to be using. Between 10 and 20, we're going to be using 10 and 20, 106. 0.6, I believe it was, if I'm not misremembering. It was. And then between 20 and 30, we're going to be using 20 and 30, we're going to be using 99.9, 99.8 it was. And then between, so the next one is between 30 and 40, and I want to use the smallest. So between 30 and 40, the smallest is again 99.8. So here from 30 to 40, I'm going to use that same height, 99.8. And then between 40 and 50, so right here, here's 40 and here's 50. And I'm going to use the smallest, which is 124.5. So height doesn't matter. So I'm just kind of drawing it, 124.5. Just helps me to kind of remember what I'm finding. You could draw it directly to scale, get crazy if you want. Between 50 and 60, so that's what I'm doing next. The smallest is 175.6. Okay, so this is going to give us the lower estimate of the distance traveled by the car. So remember that the distance or the displacement, they're equal to one another this time, is the area of each one of these rectangles that I have, and each one of them have 1 over 360 hours, right? Remember that, times 168 miles per hour. So this is what the form of each one of them is going to look like, right? So that the hours cancel out, and then you would continue on and add all of them together. So dot, dot, dot. But I'm going to be lazy, and I'm going to factor out the 360 like I did before. And now I just have to add up 168 plus 106.6 plus 99.8. They didn't ask me to draw this. This just helped me keep track of what I was doing. If you could keep track of what you were doing without drawing this, great. Um, if you're asked this kind of a question on a test and you're trying to show some work so that a person can follow what you're doing and then give you partial credit, and go along, and so you want to somehow explain to other people what you're doing, right? And so I was using my drawing to do that. Okay, so I have here 1 over 360, and then times 168 plus 106.6 plus 99.8 plus 99.8 plus 124.5 plus 175.6. I hope those numbers are all right as I was flipping back and forth on the paper. Oh, I was supposed to use the smaller. Oh, 176.1. It was bigger. Okay, good. I think I have used the smaller on all of them. I tried to. And I'm getting this 2.1508, but I did look in the back of the book and I did notice that they rounded to 3 places. So I'll round with them. I would tell you where to round. So that is this is the lower estimate, is what it is, of how the distance traveled by the race car. Okay, so using rectangles to approximate the area under the curve is called a Riemann sum. And they're going to call it a Riemann sum, I think, in the next section, but I'm going to go ahead and call it this now. And so if you use something other than rectangles, then they have different names for it, if you like. And so it really doesn't matter if you're doing left endpoints, right endpoints, or midpoints. What makes the estimate better is doing more rectangles. And so, like, they're trying to estimate the area under this curve, the area trapped by the x-axis and the curve. So you notice that this was all above. So this is the area under this curve, and right here a little bit too big on this rectangle and a little bit too small on this rectangle. Because the curve went under the x-axis. We're going to have more examples about that in the next section, going under the x-axis. Because this went under the x-axis, it actually counts as negative, as like a negative area. You're going to see that in the next section. We didn't worry about it in this section. And then here back above. And so here they have 4 rectangles, and you can really see that the area under the curve, there's a lot of space this area was under the curve but not counted. And so by using more rectangles, this is just however many that was 4, and this looks like 4, 5, 6, 7, 8 rectangles. You can see that, it's way better as far as hitting, and these are counting as negative again under the curve down there. And you can see that I'm not going to be able to count how many rectangles are here because I'm just too tired, but you can see that it's even better. I mean, it's just a wee bit too big here, and you're not missing all of that, but you're missing some down here. And then this is even more rectangles, and you can see that it's even better. And so if you took these rectangles and you went to, instead of having a finite number of them, you went to having infinitely many of them, then it would be pretty darn near perfect. And so that's kind of the idea. And they give you some fancy notation in the book that I didn't really worry about that much, but I know that some people really think it's really, 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 really critical. And this is just saying that this is the sum of each rectangle. This is the height of each rectangle And this was the width of each rectangle. And the way they've written it here without the I on it, so this is rectangle 1, rectangle 2, rectangle 3. Remember the first time I labeled them rectangle 1, rectangle 2. This is the width of each rectangle, and they're saying that they're having them all be the same width, like these are the same width. But I'll tell you that they don't have to be the same width. And if they're wanting them not to be all the same width, they'll put an I on there. So the width of rectangle 1, which is not the same as width of rectangle 2. And you can imagine it just makes it all very complicated. But I mean, as far as you can still find it, but you're having to do so much math to find it, the width of each rectangle being different. But the idea that they're wanting is that you can estimate the area under a curve by using rectangles. And what makes your approximation good is, and it doesn't so much matter left, right, or middle. What really matters is the number of rectangles you have. So as we went from 4 rectangles here to, I think it was 8 or 9 rectangles here, and even more rectangles here, and even more rectangles here, we got better and better. And they're saying that this is how many rectangles you have. So for this first one, this was 4 because I had 4 rectangles. And for the second picture, this was 9. N was 9 because I had 9 rectangles. And to make this approximation really good, I want to have infinitely many rectangles. I want n to go to infinity. And as n goes to infinity, I just want you to remember what delta x was equal to. Delta x was equal to b minus a divided by n. And if n's going to infinity, so imagine that, n's going to infinity, so it's getting really large down here in the denominator, then delta x, which is this fraction, is getting near what? Yeah, getting near 0. So the width of each rectangle is getting near 0. And as those widths get smaller and smaller, I'm getting more, better and better approximation. Okay, so that's the end of this video. I'm going to warm up my tea, eat a little breakfast, and get this loading on YouTube, and also get the next video going. Stop recording.